Hi everyone. So we're going to pick up where we left off last time, and Verena was mostly talking about decision trees. I think this echoes too much. Let me adjust this. It doesn't need to be that loud. I can talk loud. That's better. Okay, I don't like hearing too many echoes. So yeah, decision trees, and then we want to extend it into random forests and boosting and other ensemble methods. The idea being, we have many different learners, each of which individually may be really not very good, but you combine many together and do better. So it's the wisdom of crowds type of thing. Just one reminder, just start homework 3 as early as possible if you haven't started yet. Due next Thursday, 11:59 p.m. as usual. All right, well, it's almost traditional to start with an XKCD now. This one they had one about a flow chart about flow charts. Basically, you can find anything on XKCD that you want. This one was about how do you, the tech-savvy person, help someone like a grandparent who doesn't really know how to use a computer, and it's a flow chart. And I guess the idea is that the computer illiterate person assumes that you can magically just fix anything, but actually what are you really doing? You're basically looking for a menu item which is related, and then if you can't find it, then you basically Google and then tell them what to do. Did it work? No, yes, no, blah, blah. All right, so it's a decision tree. This is how to solve any tech support problem. Up to half an hour. After that, you give up. So I'm mentioning it because, just to recap, decision trees have a lot of very nice properties. They're extremely intuitive, easy to understand. You can explain a decision tree to someone who doesn't really know any statistics. They've already seen this type of thing a lot. It's easy to visualize. You just look at the tree. You can use it for classification, and you can use it for regression. So if you're doing classification, either way, you navigate through the tree, and then at the end, it tells you, if you're doing classification, it tells you which class you're in at the end. If you're doing regression, then at the end, it will tell you how to compute the average or your prediction for a continuous variable as well. Works fine in both cases. It's very flexible for what types of features or predictors that it would accommodate. So, it could be categorical, like, different regions or different political parties, and then, you could split like Democrat and Republican or, things like that. Or it could be continuous, and you can split based on, is X greater than 50 or X less than 50? So it's very flexible for different types of variables. You don't need to come up with a different method depending on whether you have a certain percentage of different types of variables. Just the, major downfall is that the predictive accuracy is pretty bad. It tends to overfit, which is not surprising, right? Because you just have this one tree, and it's first of all, the space of all possible trees you could come up with is vast, and it's hard to really think that it's plausible that your method or any method you come up with is going to come up with the one best tree. And it's not even clear that the one best tree is actually very good, right? Because nature doesn't necessarily work in this kind of flowchart type of way. Like, you start with trying to find the most important predictor and split based on that, and it's kind of, in a greedy way, and keep splitting and splitting. But it's not clear at all that that's how the future will look. That could be entirely driven by the idiosyncrasies of your particular data that you're working with. Okay, so the idea, the main theme for today is, how do you combine many decision trees to do better? So that's this idea of ensemble learning, and we're going to, go through a short introduction to several of these methods, especially bagging, random forests, and boosting. And most of the ideas apply both to classification and regression. If you're doing regression, then you would generally take a weighted average. So you come up with this ensemble of many different models, many different trees or whatever you're using. It doesn't have, this is more general than decision trees, but decision trees is one of the major cases of this, okay? So you come up with many, many learners, and then you combine them. And if you're trying to predict something continuous, then just do a weighted average. Of course, you'll have to think about how much weight do you put on each of those learners. And if you're doing classification, then you can do majority voting. But again, you still might want to put weights, right? It doesn't make sense to always do unweighted if some of them are more reliable than others. Okay, so this is an excerpt from my favorite intuitive explanation of random forests. So the idea here, well, I should say what the idea is first. Verena touched on random forest a little bit last time, but didn't have much time for it. So the idea is you start with the bagging idea, which is that you use the bootstrap to, actually I put this in the wrong order. I wanted to talk about this one. Okay, so start with bootstrap training samples, right? And we've talked about the bootstrap before. So you have your training sample, but you use the bootstrap to create many training samples, and for each one you create a tree. Because, you know, most of the algorithms for creating like one decision tree are essentially deterministic, and you do not want to rely on one tree, so therefore you need different data sets, you know, which you get through the bootstrap to get this variety of trees. That would be the bagging approach. Bagging would just mean you're bootstrapping to create all these training samples, and then for each one, you know, you develop your learner, and then you take a weighted average or majority voting. But random forest actually goes further than that. So it doesn't just randomize the training samples, it also randomizes the set of predictors that you are allowed to use, which at first sight seems like, so in particular, people typically use something on the order of square root. So if you had 100 variables and then you're doing the random forest, then at each stage when you're considering whether to split, when you're creating the decision tree for that sample, you would choose randomly about 10 out of the 100 predictors. You know, it's on the order of the square root. It's just a rule of thumb. It doesn't have to be square root. But typically that's what people use. At first sight, that seems extremely restrictive, that like you're just picking a random 10 out of the 100 predictors, and that seems like that could be pretty terrible because you're not even allowing yourself to use 90 out of the 100, and what if those 90 contained most of the actual valuable information? Seems like it'd be terrible, right? And it would be terrible to do it once, but the point is you're generating many of these. So you're actually restricting the set of features or predictors you can use randomly. So there's so the difference between bagging and random forests in this context is that you're doing two sources of randomness, randomizing the predictors you can use in generating the splits and using the bootstrap to randomize the training samples that you create. And you let the trees grow fully. You don't do pruning, at least in the usual random forest methods. So it's quite simple, and there aren't a lot of tuning parameters you have to figure out. You just decide how many trees do I want, and how many features do I want to do square root or some modification of that, and then you can run it. You lose a lot of interpretability in the sense that I can't just draw one tree for you. A forest is a set of trees, right? That's why it's called a forest. So it's this random collection of trees. So you can look at a few of those trees to try to get a sense of it, but you're not going to want to look at hundreds of big, and the trees are complicated, right? Because you're not pruning them. So you have a big complicated tree and then many of them, okay? And that's your forest. So it's harder to interpret, but the predictive accuracy tends to be vastly superior compared to just using one tree, and superior to most other methods. So it's one of the state-of-the-art methods in machine learning is random forest. So now coming back to this analogy, this is the best intuitive explanation that I've seen of it. So this is just an excerpt from a blog post, and you can read the whole thing if you want. But it's an analogy with movie predictions, and it's So it says, suppose you're indecisive. I won't read the whole thing because you can read it yourself. But the gist of it is, you want to know what movie to watch. Well, it's natural to ask a friend, right? But unless you have a friend who's has incredible insight into your tastes in movies, it's not a good idea to just rely on one friend to always tell you which movie to watch, right? So obviously, you want to ask more friends. The problem, though, is if your friends are using a deterministic algorithm to determine what to recommend to you, they're all going to tell you the same thing. So you use the bootstrap to randomize. So you give them different information, like so in this example, you tell one of them. You don't change everything. You don't lie and say you hated this movie that actually you loved. But you might leave out certain movies that you liked, and choose which movies that you're actually going to talk about, and things like that. That's the bootstrapping part. And so then you get an ensemble in that case. And that's basically what the bagging would do. But that's still not random forest, because he points out here the example, what if you loved both Titanic and Inception, but it wasn't because you're a big fan of Leonardo DiCaprio. It just happens that you like those two movies. Okay? So the problem then is if you always allow the option of choosing to split based on is Leonardo DiCaprio in the movie or not, and that's going to be a very useful thing just based on the training data you have that that seems like an important thing to look at. Suppose it's actually not so important, right? So the random forest idea is then we're going to also randomize whether you're even allowed to classify based on Leonardo DiCaprio. Okay, so it randomizes that as well. And then your friends form a random forest. Okay, so you're just asking a bunch of friends rather than just one friend, but you're not letting them all do the same thing. That's the whole idea behind random forests. So this is a picture. This I should have written at the bottom. This is from the Hasty Tibshirani Friedman book, which is the classic statistical learning book. I have the reference elsewhere in the slides. This picture illustrates kind of typical behavior of two things. One is in the horizontal axis, you're changing the number of trees. So you're doing random forest, and so you choose how many trees you want. And as you have more trees, it improves a lot for a while, and then it flattens out. So you're not seeing much gain after you have 100 or so trees, but very big gains at first in terms of the classification error on the test set. Improves immensely until you get to a reasonably large number of trees, and then you don't get any gain anymore. This M here is the choice for how many features you're allowed to have, right? We have this random set of features. And so you see the square root there is the green, which is the best of these curves. If you, P is the total number of features available that you could have chosen. So if M equals P, it's just saying that you don't restrict it at all. And then the middle curve is cutting it in half. And then it turns out, order of square root tends to work pretty well for how much to restrict it. So, of course, it will depend on, you try it out on different examples, and you're not always going to see this. So it is a tuning parameter, and all the usual advice and caveats about tuning parameters apply about how you're handling your test and validation set, but square root tends to work pretty well. Yes, question? Yeah, is there an intuition behind the square root? I would love to know one. I don't have one. Does anyone? Why not cube root or 5/8 or... I'll let you know if I figure out one, but as of now, I don't know one. A lot of the... There's a big gap between the theory and the practice in random forests and in ensemble methods in general. There is some theory, and there are people working on it, but overall, the methods, I would say the methods work a lot better than you would expect, naively. Like, you can think about intuitively why this method would give you a lot of improvements and possible gains. But it's still surprising that it works as well as it does for as wide a variety of data sets as it does. So, yeah, that's surprising. I think there is a big gap between theory and practice there. So lots of interesting problems for anyone who wants to work on. And this is the type of problem that you could explore, you know, both through looking at real data examples, or through doing simulation, or through doing mathematical calculations. And all three of those approaches could give you some useful perspectives on that. But yeah, square root. Square roots come up everywhere in statistics. But yeah, I don't have a good intuition on that one. Okay. But an even bigger intuitive question is, why is this ensemble idea a good idea at all? So Verena mentioned the wisdom of crowds, but I put a question mark because do you really believe in the wisdom of crowds? Like, I'm not sure I do. And so the first time I was reading about, Netflix Prize and other types of examples like that several years ago. Ensemble methods were completely dominant in the Netflix Prize. All the top teams were doing some sort of ensemble. That seems to be, no one came up with like one simple or even complicated strategy that's not based on this kind of thinking that it was competitive with the top results in the Netflix Prize. And I was wondering why that was, because I was kind of thinking back to this quote from Feynman. Richard Feynman was one of the greatest, not statisticians, physicists of the 20th century. And he had this example about estimating the length of the Emperor of China's nose. This is a quote from Feynman. He was talking about evaluating textbooks because he was on this committee to judge, how good are these science books that the schools wanted to use. And so he found that there was a large number of people who were supposed to be reviewing these books, but most of them barely even looked at them. And the hope was that you have a lot of people kind of doing lousy reviews, but you have a lot of people, then it's going to work out. So he said, the question is, do you want to have a few people who are going to read these books very carefully, or do you want to have a lot of people who just kind of take a quick look and make a quick judgment on the book? And so then the question is, nobody was permitted to see the Emperor of China. The question is, what's the length of the Emperor of China's nose? You go around asking everyone in China, you could ask 1 billion people to estimate the length of the nose, and then estimate average those billion things. Are you going to get a good estimate? And he's saying, well, these people don't know anything. They've never seen the Emperor of China, right? So you're just averaging a lot of junk. So is it going to work well that, even though you have millions and millions of predictions that you're averaging? It's not clear that that is useful at all. It doesn't seem like a very good idea, right? Because you don't know what kind. So in statistics, it is a general fact that if you average independent, identically distributed observations, the standard deviation is going to go down. It's going to scale downwards as square root of the number of observations. Okay, so you get more, if you combine more and more unbiased estimators, more and more unbiased measurements, and average them, you're going to do better and better, and the square root is going to tell you the scaling for the standard deviation. But there's no reason to think here that these are unbiased, right, for all these guesses at the length of the nose. It's just everyone may have different biases. There's no reason to think that the positive biases are going to cancel out the negative biases, right? And another way to say it is that if no one has actually ever seen the Emperor's nose, then you don't really have measurements, right? You just have these guesses that have nothing to do with the reality. So when I started seeing some of the successes of ensemble learning, I was wondering why it wasn't more akin to this, that you're averaging thousands of horribly weak, almost individually almost useless methods or models, and then how do they come together to get you something better? So does anyone want to try to discuss an intuitive reason why this you know, if you're trying to do random forest, why is it not the same as the emperor's nose? So, yes?
At least every model should have some measurement.
Yeah.
Not the case of,
Yeah, so over here, you never even see the emperor's nose. And for the ones we're talking about, the random forest, you know, each individual tree you're using, you know, it's capturing something. So it is based on the data, right? Here, there was no data. But the broader point of this is that, you know, combining lots of junk is not necessarily going to work too well for you. So, any other explanations or intuitions? And this also relates to the difference between random forest and bagging and boosting that we'll get into later. So we can come back to this. Okay, so let me explain a little bit of how I think about this intuitively. It's that in the emperor's nose case was an extreme case where you really have no useful predictions at all. We're going to go to talk about boosting, which is a case where you're doing very, very simple prediction methods, each of which is not very good but not useless. And I guess my initial intuition was that for like Netflix style stuff is that yes, each of these methods may be able to pick up on some interesting feature in the data and combining different models, and each of them, you know, accommodates different pieces of information. But my thought was that it was going to be swamped out by 1,000 other ones, right? Because you have like, maybe you have 1,000 different things you're averaging, and so are the other 999 going to drown out the one good thing about, you know, a particular one? But a better way to say the intuition, though, is what's going to happen is that some of these methods are actually capturing something useful in the data, right? Now, the others don't pick up on that at all, but they will tend to cancel out in terms of, you know, so one of them finds a particular interesting correlation in, you know, your movie preferences or something like that, and the others, there's no particular reason to think that it will go in the opposite direction. So, you know, if a small number of your learners pick up on uninteresting things and the other ones sort of cancel out randomly, is basically what's going on, I think. So boosting is an extension. Boosting and bagging often got mixed up, so I want to explain what the difference is. In bagging, we were doing these bootstrap to get these training samples, and they were independent, right? Because in the bootstrap, you're generating independent random draws, right, with replacement. So the with replacement makes it independent, right? So you know, generate a training set and put everything back the way it was and do it again. So it's with sampling with replacement. So independent. There's no sense of learning over time. In bagging, you're generally using simpler decision trees, not these full big trees, but you are trying to have some notion of evolution, okay? So you're trying to learn over time. So it's sequential in nature. Bagging is not sequential. It's just a bootstrap idea. Boosting, you're trying to literally boost up over time, and it's been found to most of the time be better than bagging, not necessarily better than random forests. And this is a quote from Hasty Tibshirani Freedom. They said it's one of the most powerful learning ideas introduced in the last 20 years. And, you know, right now, boosting and random forests are kind of probably the most successful overall recent methods along these lines. So this is just a general schematic of what boosting looks like. So here are the samples that you're using depend on each other, right? It's not independent like in the bootstrap. So you start with one training sample, and then you have one classifier that you're using, and then you see how well does it do, right? And then you try to put more weight on the points that it had more difficulty with, right? And then you keep iterating. I have a picture that explains it better. But you keep adapting as you go along, reweighting things. The exact question of how to reweight is the hardest part, and that gets into some math that I don't want to get into. But the general idea of reweighting should make sense, right? It doesn't necessarily make sense that you just do an unweighted average of all of your different models or all of your different learners, right? Like if you have 100 of them, don't give them equal weights, okay? Put more weights on the ones that do better and try to improve over time. So what can you do here is, well, again, you can choose the number of trees, and then if we're using it with decision trees, again, it's a more general method. You can choose the number of splits, so how big and complicated do you want the trees to be? And often with boosting, people just use a stump. Stump just means you make one split, like is x greater than 30 or less than 30, okay? So a stump tree just means you have the initial, just one split, and 2 leaves, 2 terminal nodes, and that's it. So it's the simplest tree, actually tends to work pretty well. So you're using much, much simpler trees. And then you need some parameters that control how the weights evolve. So how do you want to reweight things? All right, so here's a picture that explains it better than words. For how a boosting algorithm works, so we start with, so suppose you're trying to classify, you have these triangles and circles, and a stump is just going to, and suppose you just have these 2 predictors, just to have the simple pictures. If you're using a stump, you're just saying, okay, I'm going to classify based on is x2 greater than something or less than something, or I could have done x1 and had a vertical line. Okay, so a stump is incredibly simple. And then what happens? Well, you see, so you came up with this one, and of course it got these 2 misclassified, right? And the size here is basically meant to be proportional to weight in a certain sense of, I'll write out a little bit about the formulas later, not a lot. But bigger means you're putting more weight on these ones. So these ones got misclassified, and so at the next stage, you're going to put more weight on trying to get these ones right. But again, you're doing a stump, right? The stump is incredibly simple. So not surprisingly, this stump is going to look like it's going this way, right? Because it's putting a lot of weight on getting these ones right. That's not really a good trade-off, though, right? Because you got these ones right now, and then now all of these ones are misclassified. So that's not so good, okay? So then you're going to put more weight on these ones, right? Because you got those wrong. So it increases the weight on these ones, and then find another stump, and then you keep going like that. And then, well, in actuality, you would do this much longer, but just for the sake of having a simple picture, we're just looking at 3. Yeah, question?
Yeah, are you increasing the weight sequentially from 1 to 2, increased it?
Yeah.
3, those 2 weights are still there, but then it just looks smaller?
Yeah. So everything is sequential here. Increase the weights when you get it wrong. And then this then is the very end, and then at the very end is going to be a weighted average of all the ones you generated along the way, and it's going to put more weight, obviously, on the ones that did better. And so, even just in 3, in practice, you would do it a lot more than 3 of them. That's just for the sake of having a simple picture. But even with 3, you can already see it can generate a fairly complicated boundary, and you can do pretty well. Of course, it is also going to be prone to overfitting, and you always have to be careful about overfitting. So that's the general idea of boosting. Okay. So that was the big picture idea of boosting. There was one particular, but there are many different algorithms that you could come up with of that flavor, right? Depending on exactly how are you doing this kind of reweighting as you go along. And the most popular and successful boosting algorithm has been this Adaboost, and this is kind of a pseudocode for what that algorithm looks like. What it's saying is you start with equal weights on all the observations. So assume we have these n data points, give them equal weights, and then the question is how do you let those weights evolve over time? And you have some initial classifier that you come up with. So these capital G's are the classifiers that you're coming up with. You're going to have a total of capital M classifiers, and then you're just going to average them. This pseudocode was written for the case of classification with two groups, which we call +1 and -1. And that's just for simplicity, because then the sign function is going to do majority decoding, like positive is a 1, negative is a -1. So that's a simple way to represent that problem. Okay, so we're going to build M classifiers sequentially. And how do you do that? Well, you start with one classifier and then see how well did it do. So you compute this error function for that one, which is just a weight. The WIs are weights. So initially the weights are all equal, but then the weights are going to evolve over time. So whatever the current weights are, and this is just a weighted average of, this is the indicator, so it's 1 if it's misclassified and 0 if it's classified correctly. Because you want to look at how many of the observations are misclassified. And then this alpha M is for this specific algorithm telling you how to reweight at the next step. So what's this? This looks complicated at first, but notice that's really just the logit function that we've seen before with logistic regression. So this is actually closely related to logistic regression as well. It's just doing it in a more adaptive ensemble style. So in a sense, it's like the ensemble version of logistic regression. So it's looking at the log odds for the errors, right, misclassification. And then the key step here is the reweighting, right? So how do you reweight? Well, it's multiplying the current weight by this factor. Notice that if this indicator is 0, then you're leaving the weight alone. If that indicator is 1, it says that you misclassified that observation, and so you're going to put more weight on it, because that's when that exponential factor actually applies. Okay? So it's a specific weighting function. You know, many people have tried other functions other than looking at this particular way to do it with exponential and logit, but this has some nice properties, both in terms of the connection with logistic regression, and it turns out that it also has a certain optimization interpretation in terms of a certain exponential loss function, which you can read about in Hasty Tips, Shirani, Friedman if you're interested, but I'm not going to get into the math for that. But this particular way to do the weighting has some nice mathematical properties. More importantly, it tends to work really well in practice. So then at the end, your overall classifier is just the weighted majority voting. So that's the Adaboost. So this is just a picture of the type of behavior you see compared with, again, we're looking at the error rate, and the horizontal line at the top is if you're just using a single stump. Not surprisingly, a single stump is almost useless. So this picture is just meant to give you an intuitive picture of how well can boosting actually learn, right? So you start out with something that's incredibly simple, a single stump, okay, almost useless. But then you keep iterating this, and as you increase more and more how many stages you've gone through, the test error decreases very fast. So it's not always going to look this good, but many times it works incredibly well. And again, I don't think that the theory has caught up with the practice for this yet. So, yeah. All right, so this is just a quick example. By the way, this book, Python Machine Learning, just came out a couple weeks ago, and I've been reading it and like it a lot. So I took these pictures from there. I like this because it was just a quick comparison between bagging and boosting. The example is with classifying wine. So this is a public data set about wine, and you have different variables like the hue, the color of it, the alcohol content, and you're trying to predict, or the groups are based on where did the grapes come from, right? Different regions where the grapes could have come from. And this is just, because bagging and boosting get confused all the time. For bagging, you're using, complicated trees, and a complicated decision tree, can give you a pretty complex boundaries, but it's going to tend to overfit. And then the bagging here smoothed it out and does much, much better than any one individual decision tree. And the boosting actually gives a very similar result to bagging in this example. For boosting, that we were using very, very simple trees instead, right? So that's too simple, and then the boosting kind of adaptively improves it, and you actually get a similar result in this case. So, it's an arsenal of different techniques that can be applied. And I also wanted to show you a funny and actually important for anyone who's interested in like Kaggle competitions and things like that. I saw this very recently. It was a blog post called "Competing in a Data Science Contest Without Reading the Data." And, it said they developed a method so that so if you're familiar with Kaggle is kind of, in a sense, the successor to the Netflix prize. So if you go to Kaggle.com, and I recommend checking it out if you haven't been there before, they run many different machine learning competitions where they have some data set and there's something you're trying to predict. And they have a leaderboard where they kind of rank how people are doing. And as with the Netflix prize, there is one final holdout set that at the end to evaluate how everyone did. But the question is, why is so the leaderboard is just, the ranking of how people are doing in this competition. And the question is, to what extent is the leaderboard still susceptible to overfitting? Okay, because it's supposed to be calculating it based on, not only on the training data, right? It's already supposed to, in theory, account for overfitting, and yet in practice, it doesn't seem to do that so well. And so people climb really high on the leaderboard and actually have really terrible methods a lot of times. And so what they did in this was they actually, it depends on how often you're allowed to submit a solution for the competition. But this is showing public versus final. So the final is, the final evaluation. And so their method is completely useless. 0.5 here, means completely useless error rate. That's saying, getting it wrong. I think it's a binary thing in this example. So you're wrong half the time. You may as well just be flipping a coin. Okay? But as they submitted more and more different models to this competition, and then they were doing better and better and better without ever actually looking at the data. So this is a way to apparently do really well until at the end you find out actually it's terrible. So again, it seems surprising at first that you can climb that high on the leaderboard without actually ever looking at the data. But it's a good illustration of the power of boosting. So they called this wacky boosting. And what they were doing with the wacky boosting was they were just picked. So Y1 through YK are completely random binary vectors, okay? And they just generated completely randomly, and then saw that this function, sorry, I didn't define this S sub h of yi, but that's just, you know, measuring how well did that particular classification do. So that's what, you know, you're trying to predict the y's, and they just randomly did it and then saw how well does it do, and then let's pick the one. So SH of yi is just going to be a weighted average saying, you know, how well did that yi do. The yi was actually completely random. And so keep the ones that are less than 1/2, because we want the error rate less than 1/2, then do majority voting on that. And that actually did really well until you get to the final part, you know, with the holdout data. So it's a boosting type of idea based on this. You can read that blog post there for more details, but it's kind of striking that. So I mean, I think on one hand, this is a indication of the power of boosting, but it's also a warning of how prone it can be to overfitting. So it's a cool example. Yeah. So, okay, so that's the major difference between boosting and bagging and random forests. Random forest is just, you know, a very natural extension of when you know, going from one tree to lots of trees, right? And it gives you, you know, a collection. Oh, by the way, I should mention that these things are nicely implemented in scikit-learn, and you can run these methods and try them out on whatever data sets you're interested in without knowing all the mathematical details. No one actually knows all the mathematical details because the theory in this is lagging, as I said. And so, yeah. I think that's all I really wanted to say about it for today. So we're going to finish early today. Thanks.